Hi, I'm Ichi, a PhD student at Aalto University. I'm going to talk about button simulation and design via FDVV models. This work is a collaboration with Sunjun, Byungjoo, and Antti Oulasvirta. We introduce a novel model for describing the tactile characteristics of push buttons. Our model extends from current force displacement models and includes the vibration and velocity-dependent properties. Here is an example model. I will talk about more details later. Surrounding the model, we implemented an end-to-end simulation pipeline, which means from capture the tactility of buttons and model fitting to controlling and physical simulation on a prototype. And the final result shows simulation based on our new model achieved higher realism. Also, many interesting applications are allowed, such as optimization, real-time button editing, and button innovation. Above is the core concept. Now, let's begin with the background. Button is the most ubiquitous input component. Different buttons have distinct haptic characteristics, which is also known as tactility. The tactility affects users' subjective preferences and their performances. That's why people spend money on expensive keyboards. However, the current button design process is costly. The manufacturers have to prototype button samples in order to do any kinds of tests. So our goal is to enable button simulation and design from pure software and with little cost, which is nonetheless very challenging. For simulating a button, some sort of mathematical representation is needed. Previously, the model is force displacement curves, which captures the resisting force measured at different displacement of a press. For example, the x-axis here represents the displacement, while the y-axis is the force. And this is the model of this particular button. Here is a comparison of two common button types, just for you to have a better intuition about how to read the figure. The curve on the left is a tactile button. Most laptop keyboards and standard keyboards belong to this category. It has a rapid change of force in the middle of a press, so you will feel there is a snap sensation. The button on the right is so-called linear button. The force is linearly increasing along with the depth, so it's more smooth. If you are a gamer, the famous cherry MS red and black are this category. So the force displacement curve model shows the distinct features of buttons. However, the fundamental issue is that it's not complete. For example, the vibration near the step point and the velocity-dependent properties are missing. Hence, simulation or design based on such a simple model will lead to inaccuracy. Previous works for simulating buttons are usually based on this force displacement model, so they are limited to render only the linear buttons. And it's hard for them to handle the buttons with snap points. Also, the user's perceived realism is never tested. To solve the issue, a new model is required. Extended from the problem, there are two other engineering bottlenecks. One is the insufficient simulator frequency and resolution. The other is insufficient control. In this work, we present a model simulator separation control, which will be shown later. Our goal is to introduce a better model for buttons and achieve high-fidelity simulation by a pipeline. Additionally, a set of novel applications are enabled. Let's move on to the simulation pipeline. I'll go through button capture, modeling, simulator construction, and the iterative compensation. First, we capture the button profiles by measuring with human presses. A force sensor is attached in the fingertip for detecting the force, while a microphone is detecting the vibration sound wave. Reflective markers are attached on the sides of the keycap for the camera tracking system to capture the displacement. To synchronize the sensor's data and the motion tracker's data, IR LEDs will be activated before each measurement. After collecting a bunch of raw data, we then needed to convert it into models. There are two major things here. The first one is a set of filtering and resampling techniques to synchronize the microprocessor's data and the camera's data. These are some example output. Each frame is a force displacement response of a certain pressing velocity over one same button. As you can see here, the velocity does play an important role in determining the force responses. After this step, there are many parameters, actually around 800 parameters, for describing just one button. That will lead to inefficient design and exploration. The solution is a low-dimensional representation. We introduce B-spline fitting. The concept is to pick some control points to represent the whole curve. This idea raises another issue. How are we going to decide the number of control points? We then apply Bayesian information criterion for judge the goodness of a model. The lower BIC value is a better fit of a model. Please view our paper for more details. Then we ran the BIC calculation over all the button data we collected before. It showed that with 15 control points, the overall BIC value will be the lowest. The image on the right shows an example of underfitting, so it suffers much information loss. Here are two more examples after B-spline modeling, one tactile button and one linear button. Overall, the buttons show a good fit. Finally, combining the vibration data we derived beforehand, an FDVV model is done. After modeling, we then worked on the physical simulator. The design guidelines are as mentioned earlier. For example, it should be fully software controlled, and the vibration frequency range should be wide enough for generating rich feedback. Here, I want to highlight that everything is programmably controlled in our prototype. The video shows how the simulator adjusting from a deep button to a much shallower button automatically. The final step is iterative compensation. Every actuator has its own transfer function due to the mass. Accurate rendering of force is challenging because the function is usually unknown. The idea of iterative compensation is to minimize the effect of the transfer function by repeated trials. Every time, we started by a series of random actuation signals to drive the motor. Then, we placed the button with a force sensor on the fingertip. The force sensor would detect the force at each displacement point. The microprocessor then calculated the errors between the sensed value and the target reference, which is the model we derived earlier. As shown here, the overall error of a press is decided based on two terms: the mean difference at all the displacement points and the biggest difference. Then, the microprocessor adjusted the actuation signals according to the error level, as well as the difference at each point. The error will typically become smaller and smaller throughout the iterations. Please read our paper for more details. Most of the errors will be minimized around 10 presses, which only took about 30 seconds, so this is a very simple yet effective solution. The last step is linear interpolating the signals so that we have a wider range of signals that are corresponding to more velocity levels. As we expected, the actuation signals exaggerate as the velocity increases for compensating the effects of mass. Up to this point, I've quickly gone through the whole pipeline. All the model data of 6 common buttons and the actuation signals are released on our project page. We then ran a 12 participants user study for comparing the realism of original FD models and the FDVV models. 6 buttons are tested, including 4 very common 4mm gaming mechanical buttons, Cherry MX series, and 2 rubber dome buttons with various depths. The participants were asked to rate the realism between the target buttons and the simulation models on the simulator. Both FDVV models and the FD models are rendered. For all the buttons, the new model resulted in higher perceived realism. Then, let's take a look at the applications enabled by our approach. Our work allows efficient exploration and design. Applications include optimization, real-time design, and implementing new buttons. The first application is an automatic optimization. Here is a temporal pointing task that the user is trying to activate the button as the LED bullet reaches the center of the target. A Bayesian optimizer was used. It gathered the information of the places and tuned the model of the button, then tried to optimize accordingly. As you can see here, before optimization, the temporal accuracy is low, and after optimization, the accuracy is much improved. This is a final button design with Bayesian optimizer for a participant. You can see the tactility model is somehow similar to a typical tactile button. This design is achieved fully by the optimizer. We then ran a 10-participant study over 2 difficulty levels, and it showed that the optimized button can beat all the baseline buttons. Such optimization for temporal pointing tasks can be helpful for any games that require temporal accuracy, such as music tempo games and first-person shooting games. Of course, we can define various goals to achieve other objectives as well. The second application is an interactive button design tool. Since we narrow down every button to a few control points, a designer can easily design his own button by dragging these points. The model will be sent to a Python backend program which drives the simulator to render the tactility. If the designer doesn't like the model, he can easily modify the model again with the interface. Finally, our simulator allows innovative button designs, even the ones that are hard to be constructed by mechanical structures. For example, the button that augments the typing speed. Also, a button with dynamically returning time. This button can be used for computer games that some skills need a cooldown time. Also, this button has non-Newtonian fluid properties. It resists more when the pressing velocity is higher. This could be a possible design for avoiding error triggering. To conclude, we introduced a novel button model which has vibration and the velocity-dependent responses. We also present an end-to-end simulation pipeline. We contribute the model, the implementation, and a set of design tools for the community. The technical implementation, such as low-parametric modeling, iterative compensation, and design of the simulator can go beyond button simulation to force rendering and haptic rendering devices. All the materials, including the data and the simulator constructions, are on our project page. There are many things for future research. For example, a more clever approach to replace the iterative compensation. The vibration sound wave can be better measured and rendered with more sophisticated methods. There are more applications worth exploring. Lastly, how to fabricate a mechanical button after a model is designed and tested on the simulator is still an open research question. This is all my presentation. If you're interested in our work and want to learn more details, please visit our project page and check our paper. Thank you so much for listening.